Okay, so here in output, if we look at selective tracing, we also have the 101, so we don't really need to run it, but we could run it here. So we have our log files for 1, 2, and 101. We have the output that you just saw, which is not interesting, and we have the disassembled file. So if we run a diff output, selective tracing, it's a lot. Okay, listen. Okay, here. So we run this, and you see that the timer sees a different amount of instructions. So while one of them saw 38 instructions, the other one saw 46 instructions. So the two iteration one saw 8 instructions more. So we pretty assume that we can assume that kernel has 8 instructions, and we'll see it right now. And we also saw a different amount of loads, a different amount of stars, and a couple of stars. So if we do a diff on the output, selective tracing, okay, yeah, this is the output from this. As you can see, it's only on the right-hand side. So this is the difference between the two executions, is that one of them executed these 8 instructions more, and it executed 5 loads more and 2 stores more, which is exactly what we expected from the other one. I mean, we do the difference between 1 and 101, since we have assumed that here you can see that the amount of instructions is, in one case is 38 and in the other one is 138. So we assume that one iteration was 8 from looking at the difference between 1 and 2. And here you see that running 101 gets 800 instructions more. So basically, this is just a confirmation that our selective tracing is working correctly, that you could trace well. And with this, I end my part of the presentation. Now we'll have Paolo talk about how to simulate disk and network. Okay.
Oh, you want to go with the network first?
Go with the network first, okay?
Yes, it's more interesting because we run out of time.
Okay, so here what we're going to show is an example of how to actually set up a small cluster of 4 nodes, as you see in the slide on the left, running a simple MPI benchmark, an AS benchmark. Actually, we're running 5 of them: CG, embarrassing, parallel, etc. The one you see there on these 4 nodes. So this means, so it's a full network setup with 4 computers running their own operating system, talking to the network. Network is simulated, and they're running the MPI CH2 middleware library that is changing stuff like that. So first of all, I'm going to run all the 4 nodes on this small machine here. So let me start this first because it might take a little while to get started while I explain. In theory, you can actually run this, you can spread it out on a cluster of physical hosts. So obviously, if you want to run a 100-node simulation, you probably don't expect them to run on a single small CPU, for example, because of memory limitations. So you can actually parallelize all of this across multiple machines. So let's see if we can get this started. And right now, here, what I'm going to show in this window is the console of 2 SIG-nodes, of node 1 and node 4, where you can actually see the script being run in both executions, pinging, setting up the daemons to initiate the MPI execution, and then starting the benchmarks. Now we have to be a little patient on getting things up because obviously it's memory heavy and it's going to take a while. The mediator process is what we call the network simulator, and it has a dual purpose. The first purpose is to actually functionally implement the routing between MAC addresses and MAC addresses, and when they're sending stuff, when a node is sending a packet to the network, it's going to address another MAC address, and so this mediator network simulator is going to have to functionally send the packet to the right receiving node. And the second goal it actually achieves is to appropriately delay the delivery of packets depending on the network congestion. So in this case, we're assuming there's a full crossbar with an extremely fast network. So let me see if I can pull up some of the cluster configuration in just a second. It's coming up too. So in this case, I think we're using an extremely simple network where there's a bandwidth of 2 gigabit per second and a latency of 5 microseconds to do any point-to-point communication. But if you want to put like a torus or a factory, whatever you want, we have some ways of doing that. And if we actually look at the cluster definition itself, what you're setting up is, all the network configuration, etc., etc. Each of the individual nodes is using one of the scripts that Daniel was explaining before to actually characterize the behavior of the individual node. And if we look at the behavior of the individual node, you will see that unlike what you were showing before, we now have a NIC network. See the NIC timer here, you see now we have a simple NIC model with a delay of 5 microseconds and a throughput implementation for 1 gigabyte. All of this feeds into the network simulator. Right. As you might see here, we're also sending the output to a database, so we'll be able to show some of the nodes, statistics as the execution progresses. So we feed this to a Postgres database and we can read it back. Now let's see, these things have started. So now we should be able to actually see the execution starting. Now, as Daniel was saying before, so the two nodes run in some amount of, loosely coupled lockstep. So sorry, not lockstep, but loosely coupled quantum synchronization. So they're going to start a little bit out of order, and then as the simulation progresses, they'll actually get closer to being more synchronous. So if you look at the time here of simulated seconds, you're going to see that, for example, these two nodes are stuck, probably waiting for another node to